Welcome to this continuation of our model fitting exploration. Yesterday, we saw that if we're interested in fitting a distribution to model some of my data, then a number of things are to be considered. The shape of the distribution, indices such as kurtosis skewness. We've seen also that some distributions have power laws, which is a property typically of the tail. And another index that we can compute of the tail is the hazard rate. We have seen that the hazard rate in particular led to concepts of fat tail, which is a terminology sometimes used when the hazard rate goes to zero, when the value of x goes to infinity. We will see now today something related to that, but slightly different, which I call heavy tail. I call it heavy tail. That's a terminology that's used in the context of performance evaluation of computer and communication systems. The pioneering work is that of Taku and Crovella. Taku and Crovella did the theory, and Crovella did also tools. Other definitions exist. So this is a topic that is not so widely known, and the terminology is not always the same in all papers that we can read. So I will call a distribution, I will say that a distribution is heavy tail if there is the following. If the CCDF, the complementary CDF, decays by a power law with an index that is not too large, p between 0 and 2. If p is larger than 2, then of course we have a power law for the CCDF. We've seen, for example, the Pareto distributions have this property. But we will see that there is a fundamental difference at the value 2. There is a threshold value. There is a qualitative change of behavior when p is passing the value of 2. So we are interested here in distributions that decay slowly. So they decay like a power compared to the exponential or Gaussian distribution. The CCDF decays exponentially fast for the exponential distribution, and more than exponentially fast in something approximately exponential of minus a square for the Gaussian distribution. So those are distributions where the tail decays slowly. So that means very large values are possible with probabilities that are not astronomically small. But of course, depending on the index p, the decay is more or less fast. And if p is large, then we still have sub-exponential decay. But if the exponent is very large, it is still fast. So we're interested in exponents that are small. It can be seen, at least in many, without few additional assumptions, that if we have a relation of this kind, and if we think we can take derivatives for the equivalence here, then the PDF would be in 1x over p plus 1, like we have for Pareto. In particular, if we integrate the PDF versus x squared, that means if we compute the second moment of the distribution here, x squared over xp plus 1, p plus 1, if p is less than 2, that will give an infinite integral. So the heavy tail distribution that we are interested in are those that have here an infinite variance. And in fact, this is a prototypical case of distributions with infinite variance. Of course, there are zillions of ways in which the PDF could have an infinite variance, not necessarily by having a power law decay, but in practice, that's the only case that is considered in most of the literature. So heavy tail is, in summary, a property of the tail, which has a power law decay with an exponent that is not too fast, which is less than 2. The Pareto distribution is heavy tailed when its index is less than 2. The log normal distribution is not heavy tailed because it decays much less slower than an exponential random variable, but still its variance is finite, so it is not qualifying here. The Weibull distribution decays here at something that is perhaps less fast than an exponential, in particular if c is very small, but still is not heavy tail because there's exponential of a power will still leave always faster decay than 1 over x to the power p. So the important catalog that we have is Pareto. A distribution that's often used in data science is the Cauchy distribution. The one-sided Cauchy, we're interested here in the tail of positive random variables. The theory exists also for random variables that can take negative values, but it just complexifies, we won't see it. The Cauchy distribution has this PDF, 1 over 1 plus x squared, multiplied by a normalizing constant with support on positive numbers. And as we see, the decay is in 1 over x squared. If we do an expansion and we ignore the terms less than x squared in the denominator, we have an equivalent term, which is 2 over pi x squared. So it is heavy-tailed also. Now, heavy-tailed with p equal 1. Why do we talk about heavy-tailed in distributions? Well, first, because we do find them in some data sets, and because it leads to embarrassing results. In particular, the central limit theorem, if you remember, that we have used to explain why we have good formulas for confidence intervals for things like the mean, it relies on the assumption that the things we are aggregating, the distribution we're aggregating, have finite variance. I can rephrase the central limit theorem vaguely as follows: a sum of n independent random variables that have finite second moment, that means finite variance, and that implies also finite mean, then such a sum approximately has a normal distribution when n is large. This we've seen many times. So the question that arises here is what happens when this infinite, when the second moment is infinite, when this finite variance assumption goes away. So let's see what happens experimentally. So I did here a simulation study where I used samples of the Pareto distribution. So I did here, for example, 10,000 samples of Pareto. I did Pareto with various values of the index p. Here it's for p equal 1. And I did a histogram. That's by asking MATLAB to draw 10,000 samples of Pareto and do a histogram. Here it's not MATLAB, it's R, but it's similar. I plotted the CCDF, the complementary distribution in log-log scale. And as we know, we're supposed to find a straight line. Of course, because this is a random output and the number is large but not infinite, we don't have exactly a straight line, but we see that we have something that can reasonably pretend to be a straight line. And then I did something that may appear to be stupid, but we will see that there is value, a normal QQ plot. We know that Pareto is not Gaussian, so the normal QQ plot will not show a straight line. And in fact, we find an extreme QQ plot. We find something that is flat and then increases sharply. The boxes here are drawn by my tool, coded in R, automatically. So if the box shows a big part here that is only in part of the box, that means that there were a few values that were completely outside. For example, that's true for the histogram. The bins of the histogram have been chosen to cover the complete range. And we see that most of the data is here in the small value. And that's very typical of heavy tail. Most of the values that you sample from a Pareto distribution are small, but there are a few large ones. We don't see them because it's only 1 out of 10,000. So the Y value is undistinguishable from 0, but there are a few. So I did 3 such diagrams for one distribution. Okay. This is what we saw on the left here. Then I did the same thing for 1,000 for the aggregate of 1,000 samples here. And I did it again 10,000 times. So here, instead of choosing one point drawn from the Pareto distribution, I did draw me 1,000 Pareto samples, 1,000 samples from my Pareto distribution. I take the average, 1 over 1,000 times the sum of those values, and that gives me 1 point. And then I do it again 10,000 times. So what I have here is an empirical set of results for a distribution, which is on the left Pareto, and on the right is the aggregation of 1,000 Pareto random variables. What do we see? Well, we see that there is not much difference here. We see the histogram has the same qualitative shape. We see that the CCDF is no longer exactly a straight line. We see there is some curvature here, but the tail appears to be a straight line. Of course, there are a few points at the end because there are extremely few very large values. Those few points are very random, so we should focus on the part just before those rare points, and we see something that appears to be a straight line. And now I continued. I did it for p equal 1, p equal 1.5. P is the exponent of the Pareto distribution. Remember, the CCDF is in 1 over x to the power p. So of course, for various values of p here, p from 1 to 3, here's the value of 2, I obtained very similar things for the CCDF. Of course, we have a power law always for all the CDFs. Remember, this is random. A few of the points may show deviations, but we see a straight line. And since my plotting software also chooses the box automatically, whether depending on the occurrence of one of a few rare events at the tail, the box will be different. But they all show a power law here, which is expected because we know that the Pareto distribution has a CCDF that has a power law. Then I did the histograms, and we see that when p equal 1, the histogram is very, very irregular. Most of the data are in the small values, but the range is large. And we see that this property continues to be true, but diminishes when p gets large. So when p gets large here, the decay now is in p cubed instead of 1 over p. So the decay is still fast, not exponentially fast, but still fast. And we see something that starts looking more like an exponential distribution. Of course, it is not strictly exponential, but it looks more like this than like a strictly Pareto. And if I do the QQ plot, of course, all the QQ plots show this is not at all a straight line, so those distributions are certainly not Gaussian. This is for the original distribution. Then I aggregate them 1,000 times, and what do I see? Well, I see that what we discussed already, for p equal 1, there is not much difference. Only a small change here in the CCDF that is not exactly a straight line, but still as a straight line at the end. If we go to p equal 3, we see a radically different story. We see that the histogram starts looking like Gaussian. Well, after all, this is expected. That's the central limit theorem. The central limit theorem says that if I aggregate 1,000 Pareto distributions that have a finite variance at when n is large, so if 1,000 is large enough, we should have something that looks like Gaussian. And this is what we see visually on the histogram, and also on the QQ plot. We see that apart from 1 or 2 values at the ends, it looks like a very good straight line. Now, we see here a plot here that has lost a large fraction of its curvature. It looks much less like a straight line here in the CCDF, but this is less obvious here. And we see a continuum between the two here. We see that when p is larger than 2, it starts looking more seriously like Gaussian, and when p is less than 2, then it does not here. Well, this is illustrating exactly what happens in theory. When we aggregate, or when we do the average means we multiply by 1 over n, but this is just a scale parameter for the result, doesn't change the shape of what we obtain. When we aggregate n random variables, then if they have a finite variance, we obtain a normal distribution, otherwise not. If they are heavy tail with index p, we obtain something else. What is that something else? Well, it is called a stable distribution. A stable distribution is a distribution that belongs to a family of distributions that is much more complicated than the normal distribution. They have shape parameters that depend on p, the index of the heavy tail decay of the original random variables, which is conserved by aggregation. So we see that if I aggregate n random variables that decay in 1 over xp, and p is less than 2, then the aggregate is a stable distribution that has the same property. It is again heavy tail with the same index p here. It's not easy to show on small data sets, but here we can see it perhaps here. We see that when p is larger than 2, which are those two values here, p equal 2 is a boundary case, so it's hard to see what happens exactly. When c is larger than 2, we lose the power law decay of the tail. We start having something which looks like a Gaussian distribution, and it is indeed a Gaussian distribution in the limit. In contrast, we see it very clearly for p equal 1. Even when we aggregate, we obtain something that continues to have a power law in the CCDF. So there's a magical thing here. Depending on whether p is less than 2 or not, then we have a radical change. The heavy tail property, the decay being a power law with index p less than 2, is preserved. The stable distribution therefore have an index p, which says at which rate their tail is decaying. It decays like 1x over p. The CCDF of a stable distribution decays like 1x over p for some p. But in addition, they have also a skewness parameter, beta, which says how asymmetric they are. So stable distribution, unlike the normal distribution, are not necessarily symmetric, so they are considerably more complicated than the normal distribution. So for every p and for every beta, there is one standard stable distribution, and then all the other stable distribution are derived by change of scale and location. Now, the bad news is there's no closed form for the PDF, nor for the CDF, so they're not easy to use. That's why we don't see them very much. That's why you don't see a big data science paper saying, I model my data as a stable distribution, although probably this is adequate in many cases. But because we don't have closed form, not even for the PDF nor the CDF, it's not very easy to use. There is closed form for the Fourier transform. They are given in the lecture notes. So practical computations are based on numerical inversion of Fourier transform. But as we will see in a few more minutes, because they're hard to use in practice, we often replace them by something that is a poor man's version of the stable distribution, which consists in combining a distribution that has a normal or log normal body with a Pareto tail here. If you look, for example, at this distribution, you see here it looks like a log normal distribution in the beginning and the end as a tail. So trick that is used to make this more tractable is to model this as a combination. When p equal 2, which is the boundary case, the limiting case, the heavy tail is when p is less than 2. In the limit where p equal 2, then we have an aggregation case, which leads to normal distribution. So the normal distribution is often considered as a stable distribution with an index p equal 2. But here the decay is not in 1 over p squared. That's really different whether p is less than 2 or p equal 2. So there is this strange mathematical thing, this anomaly, if you want, that there is a threshold effect at p equal 2. Okay, let's see if you're able to address the questions in this quiz. Here I have n random variables, and x bar is the mean of those, and they are IID here. I'm proposing 3 statements. If each of the xi is heavy tail with index p, of course, less than 2, then x bar approximately has a stable distribution with index p. If each of the xi is Pareto with index p, then x bar is also Pareto. If xi is Pareto with index p, then x bar is heavy tail with index p. What of this is true? I close the poll in a few seconds. Closing. Large variance in the results. Well, let's see. First statement is true. First statement is true. That's what I just mentioned. If we aggregate n identical random variables that each is heavy tail with the same index p, with the same distribution, therefore the same index, then x bar in the limit when n gets large will have a stable distribution with the same heavy tail index p. So that is A is true. How about B and C? Well, they are not true. Well, if p is less than 2, then what we have seen in the previous diagram is that x bar is not Pareto, but is approximately stable. And if p is larger than 2, then it's approximately normal. So in both cases, it's not Pareto. So when we aggregate Pareto random variables, we don't obtain Pareto. This is what we saw in this thing here. When we aggregate on the right Pareto random variables, we don't obtain Pareto, we don't obtain exactly a straight line. We obtain either a stable distribution, for which we have an approximation here, or a Gaussian random variable, which is what we obtain. An approximation of it is shown on these graphs here. So Pareto is not conserved, but the heavy tail is conserved. The heavy tail property, the Paolo decay of the tail, is conserved, but only when p is less than 2, here in those two cases. And the last case, if x is Pareto with index p, then what happens to the limit when we aggregate? Well, if p is less than 2, the limit is normal, therefore it's not heavy-tailed. But if p is less than 2, sorry, if p is larger than or equal to 2, the limit is normal and not heavy-tailed. If p is less than 2, then the limit is stable, therefore heavy-tailed with index p. So the heavy-tailed property with power law at a rate with an exponent p of Pareto is conserved, but only when p is less than 2. So it's a bit tricky, admittedly, but this is how things are. Now let's assume I do the same thing, same question as before, but I assume that each of the random variables has a stable or a Gaussian distribution. What can I say about the limit, about the sum? Sorry. I close the poll in a few seconds. The answer is both are true. Here, B is true, we know that. A sum of random Gaussian variables is Gaussian. The same is true for stable distribution. In fact, this is why they are called stable. They are closed by aggregation. If you aggregate n times a stable distribution, you obtain a stable distribution with the same index. Well, we didn't see it, so you couldn't guess, but the explanation is intuitive because a stable distribution is the limit of the sum of a large number of n things. So think of the stable distribution with index p as the sum of n Pareto random variables, for example, with n is large. Now, if you sum 2 of those, then you can consider that the sum of 2 of those is the sum of n Pareto distribution with n much larger, at least intuitively, This is how we can think of it. So therefore, it will also be stable here. So this is why those distributions are called stable, is because they are stable, closed in some sense, under aggregation. Why do we care about that? Well, infinite variance distributions are something that should raise a red flag somewhere. If that happens, we may have problems. Well, let's see the kind of problems we may have. We may have problems, but it may also be a feature of our data, and then we need to address it. We can eliminate the problem by taking the log, for example. But if we ignore it, what would happen? For example, assume I have generated, so this is an artificial example, where I've generated a number of random variables from a Pareto distribution with this P. So P1.25, it's heavy-tailed here. And the mean that I took that I obtained here is the standard Pareto, so starts at 1. The mean can be computed in closed form. Here is 5. And the true median that can also be computed in closed form is 174. And now assume I don't know this simulator, but I just know the data. And I want to estimate the mean and the median of my data set. So the problem is I've given to you an output of my simulator, and I say, oh, that's the result of my experiment. How do you compute a confidence interval for the mean and for the median? Which of those formulas appear correct to you? I close the poll in a few seconds. Unanimity on A and B, but unfortunately here only only B is true. So B is true because, well, perhaps we don't know those formulas by heart, but if we look up the theorem, we'll see that is the theorem for computing confidence interval for the median. What are the assumptions for such a theorem? The data sequence is IID, period. For the mean, this formula is true in the sense it's the good formula, but when is it valid? When does it really give a confidence interval for the mean? Well, only if the central limit theorem can be trusted upon, which means if the aggregation of the X that we are doing here does follow a Gaussian distribution. But if for a data set that we had, it's not true because the data that we have is coming from the Pareto distribution with P equal 125, which is heavy-tailed. So it is not true that we can apply this formula here. Of course, we can apply it and pretend it would give a confidence interval. Well, let's see if we do this. Here I did it with 100 samples. So I did the experiments twice with 100 samples and with 10,000 samples. This is the data that I obtained. Now, having taken this course, the first thing, of course, I hope you do is look at the data. And if you look at the data and you see such a data sample, you see, wow, this is data that is certainly very far away from Gaussian. A few values are very large and most of them are very small. So we would be suspicious, right? Probably I'd take the log of this data before talking of any quantitative statement I want to do. But assume I don't do it here. Here I plotted on the right the result of the formula. The true mean is this blue bar here, which is outside the box. The true median is here. And here I gave the confidence intervals obtained by the method that we saw in the previous slides. So the mean plus or minus 196 over square root n, the estimate of the standard deviation. That gives something which is in this case completely off, right? The true mean is completely out, right? but the median not here. If I use the bootstrap, that does not, we know the bootstrap is a poor man's substitute to computing confidence intervals with closed form, but it doesn't work either. So take-home message here is, if the simple thing with Gaussian doesn't work, then the bootstrap might not work. Why does the bootstrap not work here? Well, because this distribution has a huge variability, and by resampling from this distribution, we don't get a good image of what the true distribution is. The number of data points here would need to be extremely large. The last diagram I did here is to look at the bootstrap estimates. The bootstrap estimates are estimates of the mean. So I do bootstrap replay experiments where I redraw with replacement 100 samples from those. I compute the mean, and I do it a large number of times, let's say 1,000 times. If the central limit theorem holds, we have obtained 1,000 samples of the aggregation of these 100 random variables. So it should look Gaussian. Here we see there is some probably significant deviation because of this curvature here that tells us it's not Gaussian. If I redo the same thing with 10,000 samples, the bootstrap estimates will clearly say it's not Gaussian, which means the central limit theorem does not hold. So those formulas still don't hold. Now the true mean happens to be here. We see that the estimate is fairly bad, not extremely bad, but fairly bad. So here we're lucky it falls in the interval, but the formula for quantifying the uncertainty is wrong. It's probably larger than what we have. And the true median here, the confidence interval, which is correct, is extremely small because now we have 10,000 samples. So that's the take-home message. When we have infinite variance, then the central limit theorem with the simple result of the Gaussian formulas do not hold. So the 196 over square root n formulas are not valid anymore. They should not be used. But for median, there's no problem. There's no reliance on such thing. Well, how do we know whether we're in such a case? I knew it here because I did an artificial experiment where I generated the data. Knowing whether we are in such a case may be a bit tricky. For example, if I look at my experimental data obtained here, do I have heavy tail here and here or here where it's not always very clear? But the trick, of course, how do we do it? Well, it is to plot in log-log scale and find the exponent of the decay here. So the value of the exponent would matter. Here, there is not a power law decay, but if we do things wrong and we would estimate a power law decay, we would find an exponent much larger than 2. So the method is this one, which is encapsulated in a tool done by Crovella, based on Crovella and Taku's method, that will plot the CCDF. This is exactly what we saw several times. And then the trick is know in which part of the CCDF we should try to fit a straight line. Given that, of course, in reality, the complete CCDF is not a straight line. We don't have a Pareto distribution in general, so we need to eliminate which part. So how do we know where to eliminate? And how do we know how to get rid of the few last points that may be spurious and might be misleading, because always the few rare events that we find at the tail are not significant? This is what the tool takes care of. So the AEST tool, for example, will do that. So by doing this plot, and in fact what is done is by doing a sequence of plots where we aggregate several times and we use the property that the index P is invariant by aggregation. So this is used to estimate the index P, and then after estimating the index P, we can verify whether there's a straight line decay. It's not completely trivial and requires a sophisticated tool. Voila, that is what we can say about heavy tail. So again, it's a nuisance, but qualitatively, it is something that it's good to be aware of, in particular to avoid making the mistake of using aggregation formulas that implicitly assume that will lead to a Gaussian distribution when this may not be true. We know also what to do when this happens. Typically, we rescale. For example, if we rescale a Pareto distribution by taking the log, then probably you find things like an exponential distribution. So changing the scale is a trick that we've often seen, and that makes a lot of sense. We will conclude this module by checking a few technical things about how in practice we handle all the elements we've seen here. So the problem that we have is, for example, I've obtained a data set like this one here. For example, this is something about the distribution of objects on a web server, and their sizes counted in bytes. The CCDF follows this distribution. Now I would like to fit this to create, for example, a synthetic web server simulator. And how do I fit such a distribution? We will see that there are two techniques that are used. Of course, we will need to see whether it has heavy tail, whether it has power law, and get all these indices. But once we have found that, we will always find that we don't find a single distribution that fits all. We will need to combine distribution. This is how we will discuss now. The first element of combination is called censoring. Censoring is the difference between reality, the real world, and the world of mathematics. In mathematics, numbers are anywhere between 0 and plus infinity excluded. In the real world, everything is finite. So for example, if we measure the distribution of files here that are transferred here in that experiment, this is online transfers, then we do an experiment for some time, and we can never observe extremely large values because our experiment has a finite duration. Perhaps we observe during 1 day, perhaps 1 week, perhaps 1 month, but in any case, we will not be able to observe anything longer than the time that we have measured things here. Assume for some reason, like in some of the references that are given in Taku's work, we think that a log normal distribution is adequate. What we have observed in reality is not a number of samples of a log normal distribution, but what is called a truncated log normal or a censored log normal that we can interpret as being the output of this simulator. Remember that statisticians think of the real world as being a simulator that's hidden to us, or at least the details of which are not all known to us. So we can think of such an experiment as we sample from a distribution, the log normal distribution that we want to fit, but we see only the outputs that are less than some upper bound here. So that would correspond to this. Nature draws things. If the thing is too large, we will not be able to see it entirely, and so we will drop it. That's one possibility to think about it. There are other possibilities. We could truncate by capping it. Say instead of delivering X, we deliver the max of X and A, the mean of X and A, but that would lead to a different model. That is not called censored data. So if I have a simulator that produces this, right, we observe only the data that are not too large from a given distribution F0 here. What is the PDF of what is produced by this simulator output? I close the poll in a few seconds. Closing. And we we see some variability in the answers. Well, this should look familiar because this is in fact rejection sampling. What this simulator is doing is draw X from the distribution and then do a test that depends on X itself. If X satisfies the condition, deliver X, else do nothing, which means try again. You will see something else, you will see nothing. So the next thing you will see is the next one that will succeed. So this is exactly what we saw as a method for producing a sample of the conditional distribution of X, given that the condition is true. We talked about such conditional distributions when we talked about the hazard rate. How can that be computed? Well, the distribution is equal to the PDF of X divided by the probability that X is less than or equal to A, which gives this formula. In this formula, there is the indicator function. F0 is the CDF, that's the denominator. This indicator function says that the PDF is 0 if X is larger than A, which is normal because we see only outputs that are less than or equal to A. We will never see anything larger than A. Therefore, we need such a constraint in our PDF. So this is the PDF that we will obtain. Why do we talk about this? Well, the reason is that if we want to estimate a distribution that has a significant tail, of course, if we're estimating a Gaussian distribution and all the values we see are if we want to estimate a Gaussian distribution, the tail decays very fast, so the tail values will not matter. But if we want to estimate a log normal distribution, the values that we have not seen that will occur with small probabilities may be very large, but they take a role in the estimation because the distribution has a tail which is not as light as the Gaussian distribution here. So the problem is estimation of a censored distribution here. And of course, what we could do is ignore the censoring. I could say, I have seen the output of a log normal distribution. I ignore the fact that there is a maximum A somewhere that I can never exceed, and I will pretend I never saw something larger than A simply because the simulator, the original simulator before censoring, never produced such a large value. If we do that, as we will see, we introduce some bias in the estimation. But the good news is the generic method we have seen for estimation works without problem. What is a generic method for estimation? Where we maximize the log likelihood. Now, the log likelihood should be that of the exact PDF. Now, the exact PDF, that's the formula here. So the log likelihood of one sample here is the PDF that we want to estimate minus n the log of the CDF applied to A, given theta, where theta is the parameter that I want to estimate. So the log likelihood will be the sum over all the data here minus this because I have n data samples. So this term is in some sense a penalty term that we add to the maximum likelihood problem. If we ignore the censoring, we will not have this term. So the problem now is to find the parameter theta of my log normal distribution, but also A, because A is now an implicit value. Perhaps I know A. In some experiments, I can know the censoring values, but most of the time we don't. So I'm assuming here we don't know A. So the problem becomes maximizing this. As we will see, it's not a very difficult problem. So first, I observe that for a fixed theta, here there is no A, and of course this is decreasing with A because this is log of the 1 over F0 of A. So the optimal solution is for the largest possible value of A, but of course there is a constraint that A must be larger than all the values I have seen. That's my censoring model. Therefore, the solution, it must be as small as possible, but satisfying this constraint. Therefore, it is the max of all the values I have obtained. So my maximum likelihood estimate of the censoring value is the max of what I've seen. As usual, the maximum likelihood gives intuitive formulas. Once we have that, then I have to solve for this optimization problem. Here, that's the same problem term I had with non-censored maximum likelihood estimation. But here now I have an additional term, minus a log f0 of this quantity. This quantity is fixed because my data set is fixed. The variable is theta, but it is a function of theta. So that adds a term to this function of theta that must be taken care of. For log normal or such cases, it can be done relatively easily, even in closed form. It's not the same closed form as the one we had if we would do a non-censoring technique, which I'm showing here. Here I have in blue the data. Here, the dashed line is the log normal distribution I obtain. That's the CDF of the data. If I do the fitting while ignoring the censoring. So I've obtained a log data from a log normal distribution, stopped somewhere. I don't say where it is stopped. I estimate the censoring as the max value. And then I do the fit that I said before by estimating this here. I obtain a perfect fit here, which is not surprising because I did an artificial experiment where the data is truly log normal. So that is, we see that the dashed line, the one I obtain if I ignore the censoring, is significantly different. So my log normal fit will not be good. I will find different parameters of my log normal distribution, and the fit is impossible to be done well because I'm ignoring the censoring. How do I obtain this fit? Well, if I want to fit a log normal distribution, we've done it already. That means we interpret the data as being the log of a normal as being the exponential of a normal distribution. So I take the log is a normal distribution, and I use the standard maximum likelihood estimate for a Gaussian distribution, which are completely straightforward, sample mean and sample standard deviation. But that gives a wrong formula here. Voilà, take home message. Well, if your data is censored because you have large data values, well, you have to ignore it. But the good news, it's easy to address explicitly. Voilà, with 2 minutes of overtime, we finish here for today. Next week, we will continue with other small but important details on how to fit the distribution when we do combinations or mixtures, topics that are also very frequently used in clustering, for example. In the meantime, I wish you a good continuation and enjoy the lab.